Okay, so now I'm going to start talking about gradient vector fields. Okay, and the motivation for this, as we'll see in a little bit, is that this gives you a way of demonstrating, or at least sort of sketching. It's like a demonstration of how the topology of the sublevel sets don't change except when you hit critical values of the level set function you're using. Okay, so let me first be precise about this notion of a vector field. So a vector field, okay, on a manifold M, right, is a function. Let's just denote that as x from the manifold to the tangent space to the manifold. Okay, that maps every point, let's say x in M, right, to a vector. It's denoted by x, little x, which is an element of the tangent space at x to the manifold M. Okay, so that's quite natural. And then if you're given a function, let's say f, which is a map from the manifold to the rails, right, and a vector field x, then we can talk about this notion of a directional derivative. Okay, is denoted by x acting on the function f. Okay, so let me say a little bit about how you can define this directional derivative. And as it turns out, the directional derivative doesn't require you to introduce some notion of length or distance, but the gradient will. So oftentimes when we're doing this, it's like in standard vector calculus. In Euclidean space, one doesn't make such a clear distinction, but we'll see in a little bit why it is that you can introduce a directional derivative without some notion of distance or a metric, but you need the metric to define the gradient. Okay, so let's see what's happening. All right, so you have a manifold M, you have a point x, you have a vector field on the manifold, if you will. All right, so you can look at sort of the integral curves of the vector field. So let's call that psi, right? So psi is a one parameter curve from the rails, it's like to the manifold with the property that, so this is basically, you know, the fact that if you have a vector field, right, you can more or less set up a initial value problem in the sense of an ordinary differential equation, and you can solve it, okay? And so this, if you will, is the integral curve associated with that initial value problem, okay? So psi at 0 is, of course, just the base point x. And then, so actually I can set it up as an initial value problem, right? This is the initial condition. And then the derivative of this function at a particular point, actually a particular time, right, is just the vector field evaluated at the point at that time. Okay, so this is clearly an initial value problem, and you know, this defines this one sort of map. It's like from the rails, it's like to the manifold. Okay, so once you have that, then you're in a position to talk about the directional derivative. So the directional derivative of f, it's like along the vector field x at a point little x, right, is just defined to be, okay, so it's sort of the obvious thing. You have f, you can evaluate it on some curve, okay, which satisfies this. So you look at the curve which actually goes to the point x, right? So, and you think of it as a function of time. You differentiate respect to the time variable and evaluate it at t equals to 0, because at t equals to 0, this is actually the point x, right? So this is the obvious notion of a directional derivative. It's like along the flow of a vector field. Okay, so it's sort of fairly clear again from this that nowhere it's like have I needed to introduce a notion of a distance or inner product. Okay, so so that's the directional derivative. Excuse me, directional derivative x bracket f. Okay, so to introduce the gradient, right, we need a notion of sort of length. All right, so to do this, we introduce a Romanian metric, which is basically sort of a smooth assignment of an inner product at every sort of tangent space sort of txm on the manifold. So what that really means, of course, is that for every point in the manifold M, right, there's a tangent space associated with it. I'm going to assign an inner product to this, and I'm going to have this assignment of the inner product be smooth with respect to changes in the base point x. Okay, so that's more or less what you have. And then if you have that, it's like then the claim is that we're going to be able to relate the directional derivative with the gradient by using this inner product. Okay. So given a smooth manifold M, right, a Romanian metric, which I denote by this inner product, right, and a smooth function f from M to the reals, right? We define the gradient of f, right, as the vector field nabla f, okay, which is a map from, again, the manifold to the tangent space to the manifold in the usual way. Okay. Okay, and it's characterized by the following relationship. So we have this notion of directional derivative. We have x, f at the point x, right? And that's something which is just a scalar value, okay? Just a real value. It's like at the end of it, okay? And then we also have another piece, which is f, and then we have, x, right, which is the vector field, x at little x, okay? And then we have the inner product, right? So the inner product, it's like takes two vectors and gives you a real number. This is a real number on the right-hand side, so I have to put something here. And as you might expect, you're going to put the gradient, the nabla of f at x here, okay? So again, if you remember from vector calculus, you know that the directional derivative of f, it's like written in local coordinates, is always something like the gradient of f. It's like dotted with the vector field, right? And so this is exactly the natural generalization of this. It's like when you have a Romanian metric or Romanian inner product, and then this is the right-hand side, which is sort of this intrinsic notion. It's like of a directional derivative, which doesn't depend. It's like on the choice of inner product, right? So, but in any case, so it's clear that it's like this gradient f viewed as a vector does depend on the inner product because it's like this thing on the left depends on the inner product, right? Whereas the thing on the right doesn't. Okay. So that's and then this has to be hold for all vector fields, right? In the space of vector fields on M, right? So this is the notation for saying vector fields. So the space of vector fields on M. Okay. All right. And then, of course, if you do this in local coordinates, right, in local coordinates, and in particular, if you do this in local coordinates where the Romanian metric is just the usual dot product, right, then, so that corresponds to sort of with sort of orthonormal sort of unit vectors, sort of, well, orthonormal basis vectors maybe is perhaps the better way to say it. Okay. Then the gradient is just the usual expression at a point x, right, is just given by again nabla f at x, right, is equal to this column vector which of partial derivatives of f respect to the coordinate functions. Okay. All right, so that's sort of the usual thing. All right, so in any case, the reason why it's like we're introducing the gradient is because it's going to turn out to be useful to grow or to give you a dynamical description of the evolution of the sublevel sets as a function of the parameter value. Okay, so we use the gradient to define or to introduce a one-parameter family one-parameter group actually of diffeomorphisms okay, phi, which is a map from the rails across the manifold to the manifold itself, right? And then so we can define a map that's phi sub t, which is a map from M to M, right? By sort of the obvious thing, right? Phi sub t of the point x is defined to be phi tx, right? So it's more or less just taking this parameter and putting it in a subscript here. Okay, and then in this map, phi t, right, is a diffeomorphism of M to itself. Okay, so that's not so surprising. All right, and then the second thing is sort of a group property so if you have phi t plus s, that's going to turn out to be equal to phi t composed of phi s for all t and s in the rails. So this is the group property. Okay. And then you can relate this one parameter family. It's like to a vector field which generates it, right? So we can relate phi t with a vector field. Okay, by just differentiating the flow, right? So if you're familiar with the notion of flow maps, it's like of sort of differential equations, right? Those are examples of things which are sort of very closely related to these diffeomorphisms. And so if you differentiate the flow map, you get the original vector field back. The same thing is true here. If you differentiate this one parameter family of diffeomorphisms with respect to the parameter, you define a vector field. Okay. All right. So, and then, so we want that this vector field be parallel to the gradient vector field. So we're going to relate this to the gradient of that vector field, and that's yeah, that's because we want to use this gradient to define this one parameter family, right? Okay, so you just take the limit as some parameter epsilon goes to 0 of f evaluated at this flow by a small time epsilon of the point x minus f at x, right, divided by epsilon. So this is just some sort of finite difference. It's like, which gives you something, again, like a directional derivative. It's like along the this one parameter family of diffeomorphisms, right? So this is a little bit like the directional derivative. Okay, and I want to relate this to the gradient of f at the point x, normalized appropriately, okay, and then pair it. So this is just a vector field now, right? And then I can act it on f. Okay, so this is going to define for me now, it's like the flow. Okay, so this group of diffeomorphisms can be used to it can basically, well, the best way to sort of think about it, this group of diffeomorphisms describes the evolution of the sublevel sets as the parameter of the sublevel set. It's like varies, okay, which is perhaps not so surprising because it's related to the gradient of the function, okay, and so that this group, so it follows the evolution of the sublevel sets and can be used to prove that there are no topological changes can happen between sort of contiguous critical values. Okay, and more or less intuitively, it follows from this fact that you know, this gradient flow, right, is only going to really define a one parameter family of diffeomorphisms. In general, it's going to define a one parameter family of maps, right? But it's going to turn out that it's a diffeomorphism if this vector field, it's like which is defining it, is well, at least it's like along the you know, it's like the points where it's evolving out of, right, is going to be sort of non-degenerate, right? Sorry, not non-degenerate, but it's sort of a regular point of the vector field, okay? So it's so when you're at critical points, it's like things can change, and so one has to be careful about it. Okay, all right. So let me say this more specifically, so more precisely. What I mean by that is that if you have f as a map from M to R, right, which is smooth, and A is less than B, such that the preimage of the interval from A to B, the closed interval from A to B, is compact, right, and contains no critical values, no critical points. Of F, right, then what's going to happen is that the sublevel sets associated with those two values A and B are going to be diffeomorphic to each other. Then MA and MB diffeomorphic. Okay, all right. So yeah, so that's basically what's happening is that you use this gradient vector field to define, it's like basically one parameter family of maps. If it so happens that, you know, it's like this doesn't involve critical values, it's like of that, then this is actually going to turn out to be a diffeomorphism, right, over that interval of parameter values. And so the level sets associated at the two end values, right, are going to be diffeomorphic to each other. And of course, everything in between that also diffeomorphic to each other. Okay, so so as you might expect, then it's like if it turns out that you know, it's like this pre-image, it's like of that interval contains critical points, then in general the topology is going to change. And so well, the next thing we'll talk about is, well, how do you actually what actually happens? It's like when you hit a critical point or critical value. All right. So I'll stop here for now.